All right, number 4. On which of the following intervals is the graph of this curve concave up? So what do you think?
Double prime.
Concave up, double prime, right? That's what you should be thinking of, a second derivative. So we're going to go, whoops. So we're going to go in here and get the second derivative. And a good place to look, not the only place, but a good place to look for inflection points is when the second derivative is 0. But it's also could be, it's got to be a change of concavity to guarantee that you have a inflection point. Now, with that said, on a multiple choice question, you're not really required to show your work except here on this review packet I wanted you to. But there it is. Set it equal to 0. Remember, those are possible inflection points. So if you factor out a 20x squared, you get x minus 3, I believe. Is that right? So either x is 0 or x is 3. Well, that's not surprising looking at our answer choices. But it's a number line that's going to tell us what's going on here. So negative 1, 1, 4. Here's our second derivative right here. So if I put a negative in, that's going to be positive. Negative 1 minus 3 is negative. Positive times negative. Put a 1 in here, that's positive. That's negative. That's negative. Put a 4 in there, that's positive. That's positive. So where do we get a change in concavity? Oh, wait, we don't want to change the concavity. It says, where's it? There we go. So it's kind of like that when's the particle moving to the right. We want a number line, because moving to the right is when the velocity is positive, left when the velocity is negative. Concave up down is when the second derivative is positive and negative. So just chart stuff here. So concave up is greater than 3. So Roman numeral 3 is the one. Okay? But if it was an inflection point question, then it would be just that one at x equals 3 would be your inflection point. All right? Let's talk about number 28 since we're recording here, and we talked about this one in the other class. And I think it's a good one to do. I don't know how many of you got to look at it yet, but no, it wasn't 28. Well, 28's okay. We could do 28. Actually, the one I'm thinking about is in the next section. Number 11. Now, it's kind of funny. I just went by number 5. Number 5 is a lot like number 11. Anybody get a chance to look at this one at all? What'd you try? Did you try anything? What'd you do?
I just put like u1, I substituted what b was, and I substituted what y was.
Now, and I will tell you, did you recognize that that's a comma there, or did you treat that as a prime?
I did.
Yeah, okay. Because in the other class, people were thinking that said v prime right there, but it is a comma. It is a comma. So you did substitution, and I think that's probably what most people would think to do here. Okay. So why don't you just take a couple minutes here and try that? Then some of you who haven't done that yet, take v equals ln x. So let's plug that in there because what they want is y prime of x, right? They want dy dx. So go ahead and try that real quick. Just make the substitution and see what you come up with, and then I'll kind of have it up here. But there's something else I want to show, another method I want to show you that's kind of interesting here. Now, this is a calculator one. However, at the bottom of this packet, what's it say? What's the copyright date? Like 1998, right? This is fairly old. I hate to say that because I bought these new. These books that these packets come out. I found out them when they were new. But anyway, so when you do here, so here's what I've written down so far. Okay, if V is ln x, then this would be ln x minus 1 over ln x, and that's u, and so you put that into the sign. So wouldn't this be correct? Wouldn't this be what we're looking at right here? Okay. So now we want to do the derivative. Now, at this point, you could, on your calculators, do that derivative right there, right? Now, when this book was written, the CAS calculators didn't really even exist. I mean, I think they were around, but very few had them, and very few, if anybody, were using them on the AP test. I think today this would be on the no calculator part. Okay, so I'm going to go ahead and go through this no calculator. But today you can just type that in, get the derivative, then you could put an e in, do your vertical bar thing and have it put an e in for you, whatever, and work it out, and it would probably go a little better. But I think it'd be no calculator. So let's go through it. So I've done the derivative. So okay, sine of this would be cosine of this, and now we got to do the derivative inside. So the derivative of ln x is 1 over x, and then how do we do this? Now careful. Yeah, we'd have to treat that as ln x to the negative first, right? You can't just do the derivative at the bottom, right? That doesn't work. That's like L'Hopital. So you bring that down, that'd be negative ln x to the negative 2. The negative would be on the outside. And then times the derivative inside, which is 1 over x, right? Which we could flip this negative power down to the bottom. We could leave the negative on top. And we have ln x squared and then an x out there. Now, if I stick that back down in the parentheses, the minus and the negative would cancel and become a plus, right? So I'd have 1 over ln x squared and then times an x down. Right? So that's what I would end up with when I did that derivative. Now, the calculator may do, may rearrange that, make it look a lot different, but that's basically what I would have. Now, it's not that bad, though, because now we got to plug in e for x, and it actually works out really nice, because everywhere we plug it in almost, you get ln e, which is, ln e is 1. So right here we'd have 1 minus 1, 0, cosine of 0 is what? Cosine of 0 is 1. So this whole thing is just 1. Okay, that's nice, times this. So now it's just this. Well, here we get 1 over e. Here we get ln e is 1. 1 squared is 1 times e. That's 1 over e plus 1 over e is 2 over e. 2 over e. So that wasn't too bad, actually, when you do that. Now, you say, well, why in the world did they do that? I mean, what's the deal with it? Substituting in. Who would ever have these 3 different functions like this? Well, let me show you where this comes from. It's partly my fault that you haven't seen something like this, because when we were learning about the chain rule, I didn't show you this because I just didn't want to complicate things any more than they already were. I thought it would be better than if we just waited till like now and look at it now. Okay, and so we're going to. So here would be the alternate form of how you could do this. Notice it says dy dx, which is telling you the derivative of y with respect to x. We don't want to do dy du or anything like that. They want dy dx. But here's what we could have done. We could have said, you know what, let's just take this function and do its derivative, which would be dy du. What would be dy du? Cosine u, right? Would we tack on u prime? No, because u prime would be du over du, which is just 1, right? We're doing it with respect to u. All right, now, let's do this derivative. Let's do du dv. Well, that would be v minus v to the negative 1, so that would be what? One plus, so it'd be, okay, so it'd be 1 plus v to the negative 2. So it'd be 1 plus 1 over v squared, correct? Okay, and now let's do dv dx. What's dv dx? Okay, now, what if you times all three of those together? dy over dx, which is what we're looking for, right? So now we need to just plug in. So we got x equals e, so right here we'll plug in e. Now, here we have to plug in a v. How will we get v? Oh, if x is e, then ln e is 1, so v is 1. So if v is 1, this would be 1 plus 1 is 2. And then cosine u, how will we get u? Well, if v is 1, this would be 1 minus 1, which is 0, so u is 0. So cosine of 0 is 1. 1 times 2 times 1 over e is 2 over e. Right? Now, so again, but it's still, the question remains, when would we ever see something like this? Well, it's really the chain rule. If you think about what we did a minute ago, now I can't go back to what we had before, but didn't we have a function inside of a function, kind of inside of a function? We had sine of ln x plus 1, we had all that stuff. It was really chain rule. Now, here's how I could have taught you chain rule. Here's how some books, when I first learned it, we learned this as well. If I had a problem, well, let's don't. Here's how I could have taught you chain rule. I could have said, all right, if we have a function like this, okay? If we have a function like this, what I could have done is said, let's don't think of that as that. Let's think of that as y equals sine u, and let's think of u as x squared minus 2x, right? And we kind of did this when we wrote our derivative rules. Remember when we wrote our derivative rules, we wrote them as like sine u and cosine u and tangent u, right? And then we tacked on the u prime kind of thing. All right, so it's kind of the same idea. So over here, what we're looking for is, we would always just write y prime. But really what we're looking for is dy dx, right? We want the derivative with respect to x is what we're looking for. So what we could have done is we could have taught chain rule this way. We could have said, well, whenever you have something on the inside, call it u and write it out. And then we could have done this. We could have said, okay, what's dy du times du dx? Well, look what happens. The u's cancel. So we could have done this and said, oh, okay, dy du is cosine u, and du dx is 2x minus 2, right? And so we could have had that. So we could have had cosine u times 2x minus 2, and then we could have said, okay, now put the u back in, put the x squared minus 2x back in, and sure enough, what do you get? Same answer. Now, do you wish I would have taught you that, or are you glad I did? Or does it really matter? Back then, I think it was just more confusing. I think if we would have talked about this with the chain rule, I thought, I just think it worked better with, hey, do the derivative outside, leave the inside alone, tack on the derivative outside, right? Without, especially when you get multiple ones, it would have been like the problem we just did. There would have been 3 different ones to do, okay? Now, I think it's important to look at this because when we get into some antiderivative situations, we are going to want to look at it this way, actually. It's going to help us make it easier to think in kind of these terms. So we will be doing some of this a little bit then, all right? But that's really what that is kind of another way to look at the chain rule, okay? Derivative of the inside kind of stuff. All right, let's see. One more. We got time for one more if somebody's got one they want to do. If not, we can move on. Oh, this 28 back here? Yeah, we can look at that. This is a little different twist on the particle one. Maybe I won't go through the whole thing with you, but I'll get you partway through it. This Tx actually means T times X. Okay, it's just, what it is it's a situation where they're not going to give us the position function in terms of X. They call it the relationship between X and T. Okay, because sometimes we can't write it as a function, kind of like ellipses, hyperbolas, sometimes those equations have, we can't solve for just the X. So here, we can't get the position as a function. So it's just called the relationship between the position and the time. All right, is that. Now they tell us that at X equals 2. Now they want the velocity, so what am I looking for here? What prime? There's no F in this prime. Did you say F? Okay, there's no F here. X prime, right? X prime. X is the position. It says it right here. X is the position, so X prime. So that's our output. T is our input. Okay? So X is the output function. That's our position. So X prime is velocity. So what we're looking for is X prime. All right. So that means I need to get an X prime in here. Well, I got to do the derivative, right? So how am I going to do the derivative? Implicit differentiation, right? With respect to T. So when I do the product rule here, which is what I have to do, derivative of T is 1 times X left alone plus T left alone times X prime. That's right. Equals derivative of X squared 2x X prime. That's right. Derivative of 8 is 0. Okay, so now you're off and running, and I'll just leave the rest for you, but basically we're going to plug a 2 in for that X, and we're going to plug a 2 in for that X, because that's what they told me right there, and I want to find X prime, so the only thing I'm missing is this T value right here. Any ideas how I can get that? Take the 2 and put it back into the original. If I put 2 back in for X in the original, I'll get T to be 6, I believe. If I put 2 back in for X in the original, I'll get T to be 6. And then it's pretty easy, and I think you end up with -1, I believe, is the right answer when you solve for X prime. Well, what the heck, we're almost there. 2 plus 6X prime equals 4X prime. 2 equals -2X prime. X prime equals -1. Right. Okay, so again, that was just a little bit of a twist on the old position, velocity, acceleration kind of thing, but not that big of a twist. So I think, again, my hope is we get to the midterm and we see a problem about particle moving on an axis, or something with the chart, some of those things that we've spent a lot of time on. Those are the questions we should be successful in. All right, let's talk about. I want to do 2 things here. I want to talk about the new theorem, last thing in chapter 4, which is really our last new thing in the first half of the class. Differential calculus. We're wrapping it up. Okay, all the stuff about derivatives, we're pretty much there. So on our theorems, if we go all the way back here, okay, so we had 2 theorems that I told you were going to, on Wednesday's quiz, you were going to have to be able to state them pretty much word for word. Now, as you're getting ready, I might just mention, tomorrow we'll talk more about Wednesday's quiz. So if you're going to be gone, it'll be in the video. But I'll give a pretty good summary right now. I'll be honest, I'm not going to say that much more tomorrow about it. But it's about the ideas of chapter 4. You're not going to have to work out an optimization problem or a related rate problem. But I might ask you about the process of optimization, or ask you about the process of a related rate problem. A big emphasis will be these theorems. So stating them, but then also like the homework was in section 4.8, you know, why doesn't this contradict the intermediate value theorem? You know, that kind of thing. Or, you know, if I'm 37 miles from home and then 4 hours later I'm 12 miles an hour from home, what does that say? What's the intermediate value theorem tell me about that? Well, you had to go through all the different distances between 36, you know, those kind of questions. Okay? That's what it's about. Short answer, true, false, that kind of stuff. And that's really it. I mean, that's really what it's about. So Newton's method, you know, the process, be able to tell me about the process of Newton's method. Those kind of things. All right? So just to review, so we had the extreme value theorem, let f be continuous on a closed interval AB, then f will assume both a max value and a min value somewhere on that interval. So extreme values, it's max and min kind of thing. Intermediate value, let f be continuous on the closed interval AB and let k be any number between f of A and f of B. Then there exists some c between A and B such that f of c equals k. Now, that's how I would want you to state it, something very close to that. I don't want you to say it's going to hit all the y values in between the endpoints. That's how you think about it to help you make sense of it. And that's how you might answer some other questions about intermediate value theorem. But if I say state the intermediate value theorem, I want this pretty much like that. So that'd be a good one to just put on a note card and just, you know, repeat to yourself so you can kind of memorize it, because that's what I'm after then. Okay? All right, so the new one today is called the mean value theorem. The mean value theorem. Oops, and I just deleted it. All right, so go ahead and write this down. The mean value theorem. So the extreme value theorem was about extremes, max and min. The intermediate value theorem was about in between, hitting the y values in between the endpoints. The mean value theorem is going to be about average. Okay, the mean value theorem, and this is really the more important of the three when it comes to theory of calculus. And we're going to actually do a problem where we're going to prove something that we've used in calculus using this theorem. But it says, suppose that f is continuous on the closed interval AB and differentiable on the open interval AB. So that's important. We've added something here. Okay? The first two theorems, the function just had to be continuous. Now it also has to be differentiable. What's that mean? Differentiable. The derivative exists everywhere. The slope exists everywhere. So there's no sharp points, no vertical tangents. Okay? So that's an extra added condition there in the hypothesis. Now the reason one of those is a closed interval and one is open is just a minor thing, but minor from the standpoint of as we look at a function, but important that you have it in there. Okay? Most functions we look at will be differentiable even on the closed interval also, but this just means it doesn't have to be, right? If we looked at an absolute value graph and just looked at the left branch of it, then it would be differentiable. And we don't even care if it was differentiable at that endpoint, you know, where the v is, the point of the v. Even though it's not differentiable there, it's differential in between there, and that's good enough for us for this. But it has to be continuous all the way to the endpoints because we have to have points at the endpoints for this to work. So we have to have the endpoints on the continuous piece, but not on the differentiable piece. So it's kind of a minor technicality, but it's important. All right, so what this says, the conclusion of the mean value theorem says there will be some number in the input where f prime at that point is equal to f of b minus f of a over b minus a. So in this one, we actually have a little formula that we can work with, which we will work with. All right, now let's review. You guys might have seen this when I had it up here earlier. What's this on this side? Slope at 2 points. We also know that as average rate of change. That's where the word average comes from in this theorem. The average rate of change between the endpoints. And the 2 points are endpoints. Notice F of B and F of A are the endpoints here. And F prime is what? That's slope at one point, or instantaneous rate of change. Now, what this is saying then is that if a function is continuous and differentiable, nice and smooth and nothing weird going on, then there has to be some number on the interior where the slope at that point is the same as the slope between the two endpoints. So the picture I had up here earlier, again, you might have seen me before I erased it. So if I have a nice smooth function like this, where the slope between the endpoints would be this, then there has to be some point in between there. Actually, in this one, there's a couple of them. There has to be some point in between there where the slope at that point is the same as the slope between the endpoints. Okay? If you want to think rate of change, another way to think about this is if I drive from here to Grand Island and I average 60 miles an hour, what do you know? At some point you had to be going 60 miles per hour. Right? So from here to here I average 60 miles per hour. At some point in time I had to be going 60 miles per hour. Maybe not the whole time. Slowed down, sped up, whatever. But at some point I had to have been going 60 miles per hour. That's what the mean value theorem says. So it doesn't sound like it's that big a deal. I mean, it's just kind of like, wow, okay, yeah, it seems pretty obvious that would happen. What's the big deal about it? Well, the big deal about it is this. It gives us an equation that connects F to F prime. And if you think about the chart, that's all the chart was. And the chart's been kind of a big deal for us. I mean, we've used ideas from the chart for a lot of things. And the chart was nothing more than the connections between F and F prime. So this equation connecting those is actually where that comes from. So let me show you an example, and then I'll give you an example of a problem you would have to do, but I want to give you an example of a problem you won't have to do, but I think it's just kind of interesting. So you don't need to write this down if you don't want to. But one of the things we got from the chart was this. If F prime is greater than 0, then F is what? Right? Now that's not true the other way around. If F is increasing, you don't know that F prime is positive for sure. It could flatten, right? You'd like X cubed. It flattens and then goes up, right? And X cubed is still always increasing. So if we flip that around, it'd have to say if F is increasing, then F prime is greater than or equal to 0, right? Okay, minor detail. But let's prove this. This is a key component of the chart. If F prime is positive, then F's increasing. Now, you guys just trusted me on that, and it makes sense. If the slope is positive, the graph's going up. Okay, that makes sense. But mathematically, that wouldn't be enough for a mathematician, right? They want to prove it. Here's what a proof would look like. And the proof would actually use the mean value theorem. Here's what a proof would say. Now, I'm not going to write it all out, but a proof would say this. First of all, let's let A and B be any points. Okay, I'm not even going to write it out. But let's let A and B be any points on this function f. So A and B are going to be any 2 points, and we're going to make sure A is to the left of B. So A comes first before B. Okay, so A and B are any 2 points on the function, and C is a point in between them. Okay? And we're going to stipulate that this is a differentiable function. If you remember, when we made the chart, we said that this is assuming that the function is nice and smooth and nothing weird going on. Okay, so when we made the chart, we made that stipulation. So we're going to make that same thing here. So it's a nice, smooth, differentiable function. Derivative exists everywhere. Nothing weird going on. A and B are 2 points on the curve. A comes before B, and C is somewhere in between. Okay, all those things we know. So if that's true, then we know that this is true by the mean value theorem. Okay, the mean value theorem can be proven. We're not going to prove it, but it's a true statement. So we can now say this for a fact. All right, now I'm going to multiply B minus A over to this other side. This is what a class in math theory looks like. You do a lot of this stuff. Not that I want to scare you away. You get in some higher level math classes and get into this kind of stuff. Okay, so I'm going to multiply both sides by b minus a. Now tell me what you know about this right here, f prime of c. Tell me what you know about it. Yeah? It's positive, right? Because that's our hypothesis. F prime is always positive, right? So f prime is always positive, so we know f prime of c is always positive. Tell me what you know about b minus a. Tell me what you know about b minus a. It's also positive. Why? Well, because we said a is to the left of b, right? We said a and b are any 2 points on there, and a comes before b. So that way, when you take a bigger minus a smaller, it's got to be positive. So this has got to be positive. Okay? So these two things are positive. So that means this has to be positive, right? Because they're equal. These two sides are equal to each other. So if this side's positive, this side has to be positive. So I'm going to write that down. So f of b minus f of a has to be greater than 0. Now I'm going to add f of a over to the other side. So now I got that. Now let's think about this. Now what are f of a and f of b? The y values at a and b. Now remember, a comes first and b comes second. And f of a and f of b are the y values. This says f of a, the y value at this one is always bigger than the y value of this one. So then it's got to be increasing, right? Remember, a and b are any 2 points on the function, any points. B comes after a. The y value, we just said that the y value on the one that comes after is always bigger than the y value of the one that comes before. That's what it means to be an increasing function. By definition, that's an increasing function, so f is increasing. So that's what a proof looks like to prove a statement like that. But without the mean value theorem, we couldn't do it. So any connection there is between f and f prime is proven by the mean value theorem, which is why it is such an important thing, because all of our optimization problems and all those things, we use those facts from the chart to be able to do those. And they all come from that theorem. So that's what makes it, in theory, a really important piece of the calculus puzzle. But for us, it's not that big of a thing. Okay, but what kind of question might I ask you on the homework or on the quiz? Well, any kind that's off the homework today. So you'll see when you get into the homework today about the mean value theorem. But one of the things that they might ask you, just a very basic mean value theorem problem, is find the c that makes it happen. So let's just write this problem down. So let's say I give you this function here, x cubed minus 2x plus 1 on the closed interval 1 to 4. Find c that, I don't know what word I want to use there. I can't think off the top of my head what they use in the homework. I'll say validates. That's not the term you're probably going to hear. But find the c that validates the mean value theorem. Find the c that you would get according to the mean value theorem. Okay? So, you peek back at what your mean value theorem said. Okay, it said this, continuous, differentiable, little formula. Okay, somebody got an idea of what we might do here. Plug in a 1 and a 4. I would agree. We're going to need the slope between the endpoints, aren't we? So we're going to need to plug in, we're going to need f of 4. This is, I think your work ought to look just like this. It ought to be just basically the formula. Okay? Now this is a no calculator quiz, but I did tell you there'll be a little bit of computations you might have to do. Okay? So 4 cubed, 64, minus 8 is 56, plus 1 is 57. What is it? 57 minus 0, is that right? Did you do that right? What's 57 divided by 3? 19. 60 divided by 3 would be 20. That's 3 short of that. 57 divided by 3 would be 19. Okay, what does that do for you? That's the slope between the endpoints, right? So what we've just found is, that's a big slope, but anyway, we've got this function that goes like this, right? Yeah, it is a cubic, right? So it makes sense, okay? So there's got to be some point in between there where the slope is also 19. So what do? Take the derivative, right? Take the derivative and set it equal to 19. Very good. I could have sworn somebody was going to say 0 because we always set the derivative equal to 0, right? But not this time. Not this time. We want to know, so we just found the slope between the endpoints was 19. So now we want to find the point in there, inside there between 1 and 4, where the slope is 19. So we do the derivative. So 3x squared equals 21. X squared equals 7. X equals plus or minus root 7. What's that, 2 point something? We don't want the negative one, right? Because we're looking between 1 and 4. So it says find the C. So I should label it C, I suppose. Maybe I should have put C in my derivative there. Doesn't really matter. Square root of 7. That'd be good enough. It's a no calculator, so you just use that one. So that means if you traced at square root of 7, if you graph this, slope is 19 between the endpoints. There's a point in there at about 2.7 where the slope would also be 19. So this work would be your proof. If it said show that the mean value theorem holds. Show that the mean value theorem holds for this function. Now, you probably should explain, to really answer this well, what else should you say here? You better say, if it's going to validate the mean value theorem, you better state that you have a continuous function from 1 to 4 because it's polynomial and differentiable. All polynomial functions are nice and smooth. The derivative exists everywhere. So you probably should state that, just like we did with the intermediate value theorem. We said, hey, if you're going to say that it satisfies the intermediate value theorem, you better say that it is a continuous function on that closed interval. All right, now let's just review that idea real quickly about continuous and differentiable. All right, if I had a function like this, that function is continuous, but it's also differentiable. Right, it's both. What about this one? It's continuous, but it is not differentiable. And then here's a great example. This is this is cube root of x. It's the inverse of x cubed. There's a vertical tangent right there. This is continuous, but it's not differentiable either because the slope is undefined right here. Sometimes they'll say smooth for differentiable, but I don't like that because this graph looks smooth to me. But it's not differentiable because it's got that vertical tangent. So sharp points, vertical tangents, not differentiable. One like this would be both. So these functions are all continuous, but these two are not differentiable. Okay. That's right. And if a function is differentiable, it's also continuous, always, right? It's like a square and a rectangle. If you got a square, you've also got a rectangle. But a rectangle is not necessarily a square. So just because it's continuous doesn't mean it's differentiable. But the other way around, if it's differentiable, it's definitely continuous. So somebody, you bring that up, and somebody in their class did ask, they said, well, so if I say that, like on this problem back here, if I say, well, the polynomials are always differentiable, is that enough? I said, yeah. In this problem, since this is always differentiable, that tells you it's also continuous. So you don't have to say it's continuous. But if you're doing the problem where you have to state the mean value theorem, you have to state both because the intervals are different, right? This one's a closed interval and this one's an open interval. So, yeah, if you're stating this theorem, you have to state both parts. But, all right. So anyway, continuous and differential. So you've got some homework here on section 4.8. I did want to talk just briefly about that number 4, the pipe problem on the take-home. I had mentioned something, and I'll see if you guys saw this same thing. Somebody in the other class was asking me about it, so I thought I would share it with you guys. Okay, That is not gonna work. I'm gonna have to get straight on. Still probably not. But, alright. Alright, so we got this 8 foot into a 4 foot, or maybe it's the other way around, I can't remember. But, has anybody gotten to the point where they tried to justify that their answer was a maximum? Has anybody done that? Because really, you should do like a number line or a list of candidates or something. So a student in the other class came to me and said that they did their number line, they worked it all out, and I didn't tell them if they were right or wrong or not, but this part they were right on, and I'll tell you this. They only had one candidate, and it came out when they did their number line, it went minus and then plus. Which means what? It's a minimum. But we were finding a maximum. So maybe you guys have already thought through. Has anybody got an explanation for that? Robbie, go.
Like the narrowest point on the corner, like the narrowest point, so that's the biggest it can be. If it is bigger, it couldn't make that part of the change.
Okay. Right. So that makes that a maximum. But how come the number line came out to be minus, plus? How come the number line came out to be a minimum?
I guess the way I looked at it is I found like how like big that line could be going around the corner.
Right.
So then it came out as a minimum because that's like the smallest part of the turn.
Okay. Yes. Yes. That's exactly what's going on. In other words, let me see if I can expand on what he's saying. When we wrote in class on Friday that the maximum pipe, because I mean, obviously we could fit a pipe like this around the corner, right? I mean, so what we said on Friday is the maximum pipe you could fit around the corner is going to be the pipe that touches in these 3 places, right? So we'd already determined that a pipe, the biggest pipe we can get is the pipe that touches in all these 3 places. So then, from then on, the problem became, okay, let's write an equation for the length of this pipe, and let's investigate all the possible pipe lengths that touch at these 3 places. So imagine yourself carrying a pipe up this hallway here. How long could the pipe be before you get to the corner? I mean, before I get to the corner, couldn't the pipe be this long? You know, way down to there. And as I get closer and closer to the corner, what has to happen? Pipe has to get shorter, right? And I think that's kind of what you meant by the smallest width as you make the turn, right? So as you get closer and closer and you're turning this around the corner, the pipe has to get shorter. And then once you get past it, the pipe could be really long again, right? So if you look at all those possible pipe lengths that can make this turn touching at all 3 places, the one we're talking about actually is the smallest of all of those, isn't it? So it isn't, that's one of the things I like about this problem is you're doing it as a maximum, then you get to the very last step, and even if you get it all worked out right, you go to justify it and you go, wait a minute, that's a minimum. You know, and then it usually kind of throws people off, like, I didn't expect that to say minimum. But it really is, if you think about it in those terms. So that might be a part of your explanation, possibly, you know, because if you are saying the maximum pipe length is this, and your justification is a number line that goes negative to positive, that's not good. You know, I mean, there better be some sort of discussion about why that is. Okay? So anyway, I wanted to throw that out there because that did come up in the other class, and it's a good question. All right. So your homework is the 4.9 on the grade sheet for tomorrow. The take home is due tomorrow. it would be nice if you would, have that worked out on separate paper. If when you come tomorrow, you've got that stapled maybe and put together. If you work the problems out of order, I'm okay with that. I mean, that's all right. I mean, don't worry about that. The cover sheet, I would like to have that on top of it, maybe stapled on top, even though you don't have any answers on that. I don't care. That's fine. Just leave them on with your work. But just you can have your name at the top of that and just put it on the cover. And then, so basically make sure you're getting that done, the 4.9 homework, those are the main things. I suppose a little bit in the packets, but hopefully you've already been doing that because we've got that third packet to kind of be finishing up. Probably give you the fourth packet tomorrow. We'll have a lot of work time tomorrow, really. Tomorrow when we come in, we'll hand that in. We'll go over the homework a little bit. Maybe take a few more packet questions, but I don't know how many of those will be, and a lot of work time on Wednesday's quiz or the packet stuff. Then Wednesday after the quiz will be work on that last packet. Thursday will be packet work and me answering questions. Friday and Mondays are midterm. Okay?
Oh.
All right. You got the rest of the time to work. Yeah. Yeah. I should. Let me go see. I think I got it. Yeah, in case people are gonna be gone tomorrow.
Alex is gonna be up.